Velkommen tilbage, og velkommen til vores YouTube-seere. Vi er klar til dagens første oplæg, hvor Jan, en ven af Lund&Bendsen gennem lang tid, vil snakke om ZIO-frameworket og vise, hvad det kan som et full-stack framework. Og det er et oplæg, som jeg forventer griber ind i sådan en af de helt centrale datalogiske problemstillinger, som jo ud over caching, navngivning og off by one, de to berømte, så er samtidighedshåndtering jo sådan lidt den hellige gral. Hvordan gør man det på en god måde? Hvordan får man lavet nogle abstraktioner, som er programmørvenlige, som gør, at vi kan lave paralleliserbar kode? Der er mange bud på det, og jeg ser ikke sådan nogen åbenlys konvergering mod en eller anden hellig sådan silver bullet ting, der bare virker til alt. Så det er i sandhed en kompleks problemstilling, og når vi nu er ude i Scala og det funktionelle domæne, så er det jo en af de løsninger, som sådan i hvert fald matematisk set har vist sig at være meget robust som hvad kan man sige, en metode til at opnå concurrency på en rimelig programmørvenlig måde. Så det glæder jeg mig til at høre mere om, Jan. Og tak for at dele ud af din store, dybe erfaring om Scala og de her high performance problemstillinger. Så ordet er dit.
Tak. I will do my presentation in English because it fits the subject matter a little better, and I think there are few people that would also prefer that. So we will today indeed look at a software architecture area called functional effect systems, which I will talk a little bit more about what that exactly is, but more specifically on how the ZIO framework represents that, and also how you can use that surprisingly well on the front end. A little bit about me. I have a background in Java and open source architectures, but have done a lot of other things on the sidelines as well. I think that has helped me find sort of always being curious, okay, are there different ways of solving this, like concurrency issues, but also bigger software systems, multiple systems communicating. Recently I've also been looking into domain-driven design, which I think helps also pull the right kind of questions out when you need to build a system, even towards the technical direction as well. Again, concurrency and how many users you need. But first, let's talk about what is a functional effect system and why would I want one, which boils down to functional programming as a concept, which basically says functions are good. We want to use those to represent our system. A function being designed as you put something in and then something comes out, and if you're lucky, if you put the same thing in, the same thing will come out again. Which every software language out there has. But let's do something very specific, which is let's consider this function itself as a value. So we can create an instance of something that represents our function. And I chose Java to represent this, since I expect most of you will be able to read along on that. So if we try and represent that, and of course in an asynchronous way, because we live in an asynchronous world, we could have an interface called comp for computation. That's just have one method, go do it, which returns us a completion stage, which is called a future in other frameworks, if you're familiar with that term, which will eventually complete with some value a. Is that clear to everyone here what that means? Okay. So now this means that now when we have an instance of this comp, we can tell it go, and it will do its work and eventually give us some value back. But we've already created some interesting properties, which means we can create this instance of the computation, but the thing itself, there's no computation running yet. So we can change our mind and say, yeah, I don't need it anyway, and we haven't really done any work yet. But we can also invoke Go several times, right? What would happen then? Well, it would maybe run several times in parallel, or it depends a little bit how you define that. But you have many ways that you can shape this into something fun. And one thing you can do is say, well, now we have this interface, but which method that we need to implement, like how do we do our actual work? But we could define some methods of ourselves on any instance of comp where hey, if we know how to do some work and eventually give us some value, well, we probably also know how to first wait a little bit of time and then do our work to return the value, right? You can imagine if you were implementing this in Java or in your framework of choice, if I had to implement, okay, I give you a computation, and then you need to return me something that first waits and then does that. You could do thread.sleep in Java or use a wheel timer or something similar to postpone that. Similarly, you could, in a general way, implement a repeat function that says, okay, do this computation several times, and I don't know, give me the last result that you made, assuming there's something useful that would come out of that, like retrying an API or something like that. That means that if we now have a computation that is called create user in DB that returns us some integer, maybe it's the ID of the user that the database made up. Now we can already do something more out of that, which, for example, is create another computation that will create 3 users for us instead of 1, by just saying create user in DB.repeat 3. And we don't need to write any extra code for that, so we'll just do it 3 times. Or we could combine the 2 combinators we have here by saying, well, let's create something that waits for 1 second and then creates the user and then does that whole thing 5 times. It might look a little bit contrived here, but as you go into real-world problems, there are very often things that you need to combine that come from several sources that you want to do in parallel or together or retry. And having these kind of combinators right there in your programming model can make a lot of sense. And remember, at this point, at this line of code, we haven't actually created any users yet. All we've created is a recipe, a comp instance that if we say go, then it will go and create some users. Any questions so far? Yeah.
You did mention the reactive framework in Java.
I did not mention any reactive framework in Java.
I mean,
yes.
you're essentially describing reactivity.
That is true, yes, but I'm trying to keep it as low to the ground as possible. But yes, there are a lot of reactive ideas in this for sure. Yes. Now, a function that just gives us a value is not, how do you say, it's a little difficult to make useful because there's no input that we can give it, right? Remember, our Go method didn't have any arguments, so it will just have to make up its own value every time. So let's fix that and say, well, our computation actually would need some sort of input. I called that input dependencies because that's what ZIO calls it, but you can call it the input or arguments or whatever you wanted. But let's add that to our function and say, well, now our computation, it's generic in 2 times. Some input that goes in, our dependencies, and the value that comes out. And now we can do a lot more because now we have some actual function type where we can give it arguments like what user would you like to create, what API would you like to look up, or what kind of object would you like to draw. Which might raise the question, like, what do we now do if we don't really have any dependencies, if we really have a function that will just say, do it? Well, then we just pass in anything, right? We use what's called the top type of our type hierarchy. In Java, that's object. In Scala, it's any. In most languages, it's one of these 2 terms. So you just put that in. And if you have multiple dependencies, there are a couple of solutions. Some languages offer you the ability to say, well, I want something that has this type and that other type. Java has that to a little bit of an extent as well, but Scala and TypeScript have it directly. But if anything else, you can just create a class that combines the 2, like a tuple or a record type in Java. However, things don't always work as we've all tried. Things go wrong in computer systems, and that has often led to in programming languages being said, okay, well, if you call this function, if something goes wrong, there's this thing we call an exception that might occur, and then you just deal with that, and it almost never happens, so we call it an exception because it's an exceptional thing. We don't really need to worry about that. To me, that's maybe the biggest misstep we've made in language design, calling an exception, because it's actually an extremely important part of your system. At least for, I'm sort of separating errors into 3 kinds here, for errors that we kind of knew they were going to happen. If I call a REST API, it's going to happen that the server is down, right? That it's, anything from the thing rebooting to somebody tripping over a network cable to somebody mistyping the host name or it never responding at all. So we kind of know that is going to fail. And that happens for a lot of other things as well, disk access, divisions by a number. You know that if you use your experience, you know it's going to fail. But what if we don't want to use this vast experience? We want to see that it's going to fail. Well, Java has an answer there. It's called checked exceptions. That didn't really work because it's really irritating to work with. But we want to do something there. However, we need to be fair, and there are other kinds of errors that can also occur in our program, which is things that we really didn't see coming. Any kind of bugs that crop in, but you could have a division by 0 or a null pointer or something else. Those we still need to be able to deal with somehow. But there can also be fatal errors, like the Java virtual machine has no more memory, or the disk space is filled up, or whatever it is that you can't really deal with. And what's important to realize is that you can actually explicitly deal with these things separately. Well, number one, if you know that it's going to fail, that needs to be visible somehow, right? You checked exceptions or whatever we're going to do instead. But we still need to deal with unchecked stuff as well, right? There's still going to be bugs. But the fatal ones, it might be a good idea to just, if we're out of memory, what are you going to do? You probably just want to do a memory dump and shut the thing down, which actually modern JVMs can much better be controlled to actually do that. But again, that depends on whether you are in Java or in a different framework. But keep this kind of separation in mind. But let's see how we can at least deal with our known kinds of failures. For that, what we can do now is be fair and say, well, our function, our computation, is going to eventually finish with either some result, some success, A, of type A. And we say, well, if it fails, let's say, well, how am I going to represent the thing failing? Well, we can just use a type for that, right? Doesn't have to be an exception, just any type. And then I'm writing here either E or A. Who of you have not seen the type either before? Okay, okay. So either you can see as something that is one of two values that have a different type, which are typically called left or right. So if you think of an interface, either that only has two implementations, a left class that has just one value, which is an instance of left, and a right class that is an instance of right, that's sort of the data structure that you have. And then you typically have a bunch of combinators around that says, well, was it a left or was it a right? Was it a success or a failure, and ways to deal with that. But it's a way to represent that this computation that you have, if it completes, is going to be one of two types. If you think of a concrete example, if you load a user from a database, then you could describe that as, well, that is either going to give me a user object or a string, where the string is some description of the error that happened in the database. And by representing your return type of the function that way, you force the caller of that function, or the computation in this case, to explicitly check, okay, was this a success or was this a failure? Because you can only get to the user object if it was an instance of left in this case. If it was an instance of right, there is no user, but instead you have the error. And of course, you need to make this comfortable to use from a API perspective. Even in Java, you can do this. There are libraries that implement these kind of constructs quite nicely. We do need still to represent what happens if there is no failure. For that, we have to have what's known as a bottom type in our language, which Scala and Kotlin actually as well, TypeScript has it, Java still doesn't, which is kind of saying, well, this is a class that is actually a subclass of all other classes. If you know, who knows object in Java or in .NET? So that's the superclass of everything. Nothing is a subclass of everything. So it means that if you can return nothing if you want to complete something, but it has this kind of a special property, which is that there is no value of it. So it only exists on the type system. So if you know that something never ever completes, or in this case, it never creates an error, you can put nothing there, and it will sort of fit in with other calculations. Now, if we have defined or redefined our computation like that, like it may create an error, or it may return an error, or it may return an actual value, we can again add some combinators on our comp itself. For example, if we want to turn a computation that might give you an error E into a computation that never completes with an error, so with a nothing type here, we could write a function called catch-all, which says, well, if we now take this E type that we have, remember the string that with an error message that we got from the database, if we now give you a function that can turn that error into a normal value, well, then we can never have an error anymore, right? That's at least not an expected one, because we just call that function that turns any E into an A whenever we get an error. But now we have something that will never give you an error. Of course, implementing that is going to be tricky for our user example, because what are you going to do? Make a database exception or a database error into a user. But in a general way, you certainly could do that. As an example here, we actually we have an example here, fetch user, which gives us a computation that does not have any direct dependencies. It's, as an error, gives us a db error object, which is something a little richer than the string I mentioned before. Or it gives us a user object if it actually worked. Well, we could say, well, fetch or default, like get the user or give us some default user if something went wrong. We could create an instance of that, which would be of type any no dependencies, no errors, and it always gives us a user by saying, well, we try and get the user, but if we got this db error object, then we create some default user instead, whatever that means. All right, at least from a type system perspective, we've now promised that we never fail here, and we don't have any errors, so now we can use that in further calculations, assuming that no errors occurred. Of course, for the type 2 errors, the unchecked exceptions, you could write similar combinators that say, well, if an exception occurred during any of this handling, do this instead, or convert that to a result, or convert it to a different exception. Any remaining questions? Let's continue. Now, just one function doing a little bit of work is a little boring. So let's find a way to chain functions together and say, well, let's do some work over here, and then let's do some other work as well. Typically, these kind of combinators are called map and flat map in functional terms. So let's define something that says, OK, I've done this computation, and now I want to do something else as well. So we're inside computation that has R as dependencies, and E as error, and A as success result. And let's say that I have a function that can turn any A into B. A function being a normal Java lambda function, right? You use one argument and you give a result. Well, if we call that function when we're done with our work, we now always have a B value instead of an A value. So what would come out of here is a computation that still takes the same dependencies, because we haven't changed that. Still has the same error, because we're actually not doing anything with errors in this particular function. But now the result type is B, because our function turns any A value into a B value. So using this, we can have our computation and then run a little bit of extra code that turns an A value into a B value. You with me so far? Mm-hmm. But we can make this a little bit more interesting by saying, well, let's have our function as input still take the A, so we run this function as a result of our computation. But what comes out of this function is not just a B, it is some computation that gives us a B. Since that allows us to go in and call to other frameworks or to other parts of our library or anything that creates or a computation value or something that we already have lying around. And we want to say to our system, well, after we're done with this computation and we have our value A, then go in, call this function, and then we get a new computation. I'd like you to run that. And when that one completes with a B value, then consider that the result or the successful result of our original computation. And that is called flat map, because you, inside your function, refer to other computations that you again, typically get from other parts of your code base. Like you're inside a business service and you need to load a user and then send an email out or something. Just chaining normal behavior together. But see how the errors here are still preserved. You can expand this type signature a lot more to deal with that as well. But in this case, we say, well, our initial computation is allowed to fill with an error e, which I didn't go into that, but if it fills with an error e, it's obviously not going to invoke this function because there was no value a ever, right? We just got our error, and that is going to fail. But the computation that we chain into is also allowed to fill with that same error type e. So our error type doesn't change, but we still have visibility on whatever the error type was is still going to be the same, even though we do extra work after that. I'm going to skip over this one, do this little example first. So remember our create user value that we had before, which is a computation which, why does this give us a, oh yeah, which we've expanded on a little bit. There's now a dependency that it needs, which is a database connection of some sort. If you've worked with any relational database, you typically need a transaction or a connection or something to, like a handle to what you're working on in there. And then after we've created the user, it might either fail with some database error because we've typed the table name wrong again, or some integer that gives us the ID of the user that was created. So this is our value, our computation that we can invoke if we wanted to. But now let's say that we have a method called send system mail that sends out some sort of administrative email with some message in it, which needs a mail connection because email also needs connections, SMTP or something similar. In this case, we say, well, it can't fail, or if it does fail, we ignore it, and there's no results. Unit is the same as void in Java, saying, okay, we don't care about the return value, we just care that it has succeeded at some point. Now we can use flatmap to say, well, if we want to do both, so we want to create the user and then, if successful, send a mail, we can create a value that represents that computation, which is create user in DB, and we invoke flatmap to say, hey, as a result of this, I want to do some other computation, which is a lambda function, in this case, where we take the result, which was the ID of the user, remember? And we invoke send system mail with a little message that says, well, we've created a new user. That's all well and good, but we've jumped over something here, which is that, remember how we looked at flatmap in our definition? We said, well, this error needs to be the same, right? We said this function that we put in needs to give us a computation with the same error. I didn't explicitly say, but the dependencies also should have aligned because we don't really have any rules on how this should combine. But they don't combine here because our create user in DB has DB connection as a requirement, but our send system mail has mail connection as a requirement. So what do we need as a requirement if we want to do both? We need both, right? We need both a DB connection and a mail connection. If we look at the errors for a moment, if we look at, okay, how does our create user in DB fail? It can fail with a database error. And how can set system mail fail? Well, we promised it would never fail. So if we combine those two, what kind of failure can we expect if we do both? Well, it can either fail with a DB error or with nothing, which is just a DB error in this case. But they're different operators on types, right? If we look at the dependency part, and I'm using a syntax from Scala and TypeScript and others here for the way to combine types here. It's called an intersection type, but you say, okay, I need both of these things as our dependency. And for errors, I need either. I might see either of these as errors, which is typically written as a pipe symbol, so a bit like an OR operator, and it's called a union type. But in order to write these kind of expressions, we kind of can't do this in Java because neither of these exists very well in Java. So we kind of need to make a step forward to at least a language that does support these constructs. Do you see the move we're making here? Okay, we can't express in Java the concept of saying, well, I need this type and that type. If there's time, I have a little bit more about this particular decision, but I just want to see how we're for time as we go forward. So we'll move to Scala from here because that is the
What if you have two interfaces and implement both? Wouldn't that be the end?
Yes, it is. So okay, the explicit limitation in Java is that you can implement two interfaces for sure, but they have to be interfaces, and it doesn't work with generics. So you cannot express in Java because if you look at comp type or like here this interface, these things, this R and this E and the A, they're just letters, right? I'm not telling Java that this needs to be interfaces. You actually can't tell Java that. So there is no way in Java to say, okay, I have this A, and I want to return something that implements A and something else. That you can do, but then the and something else needs to be an interface because you can only implement interfaces. And that is sort of...
When you have a functional interface, then you can have methods on it, and I mean, you could do this in Java.
Well, your methods still... the methods don't help you here because it's the types that...
Return A or return B, right? But, okay.
Yep, okay, you can push this a while. Let's look at this offline because I actually have a, how do you say, a small Java layer on top of ZIO where I'm actually looking into this. But let's take that offline because there are some interesting things that you can push and some surprising things that work and don't work. But so, ZIO being in Scala, let's look at this from the Scala perspective where we can express these things. Don't be too carried away with the syntax. This is still methods and an interface. An interface in Scala is called a trait, and methods are just written with def instead of the return type. So a ZIO in Scala is just like the computation type we saw before. It has 3 type parameters, some dependencies, an error type that might happen, and a success type that will happen if the computation was successful. And it has exactly the methods that we've talked about before. Every ZIO has a .repeat method that you can give it an integer and it will repeat it a couple of times and return the last value. It has a way to delay the computation. It has a way to catch exceptions. Additionally, it also has a way to put in these dependencies so that we can have a way to say, hey, I have a DB connection or something that create a DB connection over here, and I have a way to create a mail connection. Please put these two together and use that as the dependencies for the ZIO. And now we go to a way that specifically the Scala language makes dealing with this abstraction a fair bit easier, which is that you can hide away a lot of the types that you don't need. Because you might have started to go around and you had to say, oh, geez, we have 3 type arguments for every time we have something in our code tree. Doesn't this get a complete mess of types? And it doesn't, for 2 reasons. One is that you just like in Java with var, you don't actually have to specify the types a lot of the times. Even for functions, the compiler can derive the type for you. But most useful, you can create type aliases and say, hey, if we ever have a ZIO that has no dependencies, it has no errors, we say nothing, and it just gives us a result I'm going to call that a UIO for unfallible IO. So something that will never fail and just give us a value A. Now we suddenly only have 1 type parameter, which is just like our future looked like in Java, just a 1 type. But now it's a lot stronger because now it's not just something that returns a value, it's something that we know will not fail, at least we promise that it doesn't fail, while trying to create that value. Or I can create an alias for something that doesn't have any dependencies, but it can still fail. And you see you can sort of mix and match there. You can create your own aliases and they will sort of interoperate. Yeah, any questions? Yeah.
What is the ZIO? Is that like a general concept? Is that a Scala thing? Or is
a ZIO is a library. Okay. So Scala is a language, and ZIO is a library that creates a functional effect system for Java. So ZIO is the type. Here, this trait ZIO is in a package. ZIO. You can sort of read it like this. So this is defined in a library that you can import, and then you can make use of this, right? Just like you would use any other jar in Java land. Okay, sure. I want to mention a couple of other things just briefly on ZIO, because that is what, this is, until further, what you've seen is just an abstraction where you might think, okay, what do I get out of it? And it turns out that representing your errors and your dependencies that way can give you a lot of quality and safety while developing systems. And the biggest aspect, and we won't go into that a lot today, is that you can imagine that if you have your computation where you can control when it runs and how it runs, that if you have to distribute that computation on eventually your thread pool or your worker or your new green threads in the JVM, you can get a lot of advantages in placing things in the right way. And ZIO has a concept called a fiber, where you can actually control the execution of your computations and cancel them. Have any of you worked with futures in Java or futures in .NET? Who of you have ever tried to cancel a future? Yeah, I can see the question. I see in your expressions a comparison between can you actually do that and what actually happens. No, not in Flux, in a plain Java future. Okay. So the problem with futures is that it is not terribly well defined what happens if you cancel a future. Most specifically, if that future is doing anything with resources, they are lost. If it has opened a file, then it's up to that particular future to deal with that. And going to the second aspect that I wanted to mention, which is a scope, which we'll go into a little further. In ZIO, you can actually, in an asynchronous way, say, hey, I need to use this resource, for example, a file or a database connection, and I want to make sure that this connection goes away after I've done my work, because that's the only way to guarantee that we don't leak anything. And it's actually quite hard to do asynchronously, because in order to write asynchronous code in Java or Scala or most other languages, you need to use lambdas, right? And depending on the language used, there might be tricks to make that more palatable, but in the end, it's all functions. So you can't use something like try-catch to chain these things together. And even if you could, try-catch is also a little bit like checked exceptions. It's fairly verbose. But ZIO gives you something that actually guarantees that resource safety is upheld even if you cancel something. The fibers themselves are resources. So you can create a background process that is tied to your scope as a resource, and that will automatically stop if you stop that scope, together with closing any files or other aspects. Let's actually get into that a little more in detail. So the scope concept or resource safety basically deals with, okay, I want to make sure that some resources are closed when we're done using them, our file or our database connection. Now, if only we could express that a particular computation or an effect should only run given that we have a way to have a place to put things that need to happen when it's done. But we have a way to express that. That's our dependencies. What if we have an item in our dependency that says, hey, I need to have the ability to clean up after myself after I'm done. And then, of course, have the framework guarantee that actually happens. That concept is called scope. Scope is something you can add as a dependency to a ZIO, and then that particular computation can say, okay, I want to do some cleanup work, which is guaranteed to happen before I'm considered actually done. And in that way, if we skip over the definition, if we look over here, we can say we have a method openFile that can open file with a particular file name, returning a ZIO that now needs a scope, because that scope guarantees that we can close the file when we're done. And of course, it might fail with some file error, and otherwise you get a file object that you can use to do stuff with. Now, one of the ways that you can actually open a file, remember, we need an instance of scope to run it, right? We can't just say open file go, because the compiler will say I need an instance of scope to actually start this. And one way to do that is the scoped operator from ZIO, which basically will create an instance of scope We see the definition over here. It will create an instance of scope, and as argument, you can provide a ZIO that needs a scope. So it will take that scope, put it into ZIO, and run it with it. After it has completed running, it will tear down that scope. So anything that ZIO has said it needs to have cleaned up will be cleaned up. And then the return type is just a ZIO which has whatever other dependencies that the ZIO that we put in had. So that's just you can compare that with try finally in Java, where you run something and then you clean up. But the nice thing is that scope is just a class, just an instance like anything else. So you don't have to wrap it in ZIO.scope. You can control yourself when you create a scope, how long it will live, when you clean it up. And that means that you can put that cleanup action higher up in your code. You can combine different things in one transaction or in one connection, or you can have it maintained somewhere and delete it after some time. You can move this scope around, and it's up to you to. It can be up to you to delete things. So that's actually a very flexible way to deal with resource safety, and we'll see this come back as we continue. Any questions on that? Yeah, sure.
What's the name ZIO standing for?
Yeah, that's a really good question. I actually, I don't know. It might be a wink to ZFS, the file system, which used the last letter in the alphabet to indicate, well, this is the final word in file system. As in they feel that this is the final word in functional effects system. Turns out it might be the first word, because what's actually happening now is that people having used ZIO that find themselves in other languages are implementing the same things. There's now ZIO-ish things in, I've seen one in TypeScript, I've seen one in Kotlin, I've seen one in Rust even. It's like, and it of course only halfway works because they don't really have all the features, but people try and do the same thing, and it's just seeing where it lands, and it's fine because it's good ideas making it across languages. Yeah.
It may have lost the meaning.
It may also have lost the meaning. Yeah. I don't know the final answer, unfortunately. Yeah. Right. Let's see. Yeah. So let's see. Okay. So things we've seen here. We've seen a couple of hands in the start. Like there are actually quite a few front-enders here, but the stuff you've seen, you might classify it as boring back-end stuff, database connections and mail servers, and we don't do that on the front end. So I just wanted to show a little bit like the kind of demo application that I've been working on as a case for this, which is like a online whiteboard thingy where you can move icons around, you can draw stuff. There's some context-sensitive shortcuts here, and you can. And this is how do you say, real-time interactive. So if other people go into the same URL, they will see the same changes you're making. So not trivial. There you can see, okay, there's some work to do in setting that up, but also not complicated enough that there's a lot of UI work going into it. And that's sort of been the driving case to see, okay, how can ZIO help building something like this? Obviously, the backend is also built using ZIO, but we'll look a little bit at the front end side of things for this. Now, this part might be subjective, so if any actual front enders here say, well, this is completely ridiculous, please raise your hand and I'll I'll gladly change my mind. But when doing this, I thought to myself, okay, so actually I found out that ZIO has a branch, or rather as part of it, it can compile into something called Scala.js, which is a Scala cross-compiler for the front end. So any Scala code you can actually compile to be JavaScript-ish, and it will run in some shape or form on the web browser. Not as WebAssembly, so like actual JavaScript. And ZIO has chosen to be compatible with that, so you can use all or most of it just as is on the front end. So I figured, okay, what would we need in doing some front end work with this? We'd need some way to define a building block of making modifications to our HTML and our event handlers and other things that happen, right? Adding and removing elements needs to happen as well. Maybe they also should go away when we no longer need them, right? As you see, there's a lot of context-sensitive stuff that happens there. It would also be nice to have some abstractions for more communicative things that you typically need on the front end, like making REST requests back to your server, maybe using WebSockets as well to get some eventing going. And we might actually want to store some data in the web browser as well, which these days you use indexed DB for. But who of you know what indexed DB is? Very few, good. Again, please correct me if I'm wrong here, but it's the latest way to have a database-ish thing in the web browser. And if you've ever used SQLite, like an embedded SQL database, it's nothing like that. It looks like it. It looks like somebody has seen a database like 10 kilometers away in the distance, where like a crossbreed between SQLite and Cassandra, and then made something that doesn't look like either of them. It's really weird. But we need to use that to store stuff. It's a little bit like a key value store of sorts. And yeah, so let's use Scala and ZIO to make that up. Which brings us to a fairly important architectural decision when you make front-end things, which is virtual DOMs. So DOM is the document object model, like the HTML tree with all its Christmas stuff that goes on in there. The idea that came up, I don't know, 10 years, 15 years ago, was, hey, somebody read about functional programming, I guess, and thought, hey, what if we had a function that takes all our application state and turns that into HTML in a sort of as pure as possible way? It's kind of nice because that means that, well, if I make a chat room application, right, you can see at our application state is a list of messages, and I just create one div element for each message, and if there are more messages, I just only change my state, like I have now an extra element in that list, and then the function stays the same, and then the HTML can be created that way. It's generally a good idea. Also because functions compose, you can just write smaller functions for smaller building blocks, etc. But it turned out that it gets kind of slow, because if you just do that, and you say, well, document.innerHTML, which is the way that you can create new HTML, one of the ways in the front end, requires the browser to throw away everything it has and create a whole bunch of new HTML elements and do its layouting and other things, and that gets really slow. And many front-end frameworks instead say, well, we're still going to do that, but instead of allowing this thing to create actual HTML, we allow it to create fake HTML. So we have our own tree with just objects that are called div and input and whatever other tags you have. And then the framework goes in and checks, oh, okay, so we have a missing div over here, and we have an extra one over here, so I'll actually create one there. And it sort of tries to fill in the gaps and make that work. Which, sort of works, but it can be a little leaky, because it's not really a one-way street. It would be if all you're doing is show, a user manual or something, then it's just there. But applications these days are interactive, right? People click at stuff and stuff changes, and they edit stuff in input fields, and that's not really a one-way street anymore. So rather than trying to solve that, and actually inspired from a different front-end framework called Laminar that I did know from Scala, and I think there are several JavaScript frameworks these days that also try that. Let's just say, okay, let's push the requirement to not update stuff that's not changing a little higher into the application code, because depending on your architecture, and we're inevitably going to talk about event sourcing, because I talk about event sourcing every time, it might be easy to follow along what has actually changed and actually use that knowledge while updating things on the web browser. So conclusion, we don't have a virtual DOM, so whatever we do is going to change the DOM tree directly. Now, for our building block, we want something that can perform certain changes at a certain point in our DOM tree. The name for it, let's call that modifier, because it sort of modifies something in its parent, which it needs, and that needs to be a DOM element, which is the type you see over there. And it might be creating some child elements. It might also not, but for the ones that do, it might be useful to know the type of that as well. So let's give it some type T. And most importantly, let's bring in scope so that we can say, hey, if we create any child elements or we create any event handlers or do other fancy stuff, we want to be able for that to go away automatically. Scope is cleaned, and whoever is cleaning that. So let's say that all of these things need a scope as dependencies as well, which we can wrap up as an alias, again, a type alias from ourselves, a modifier that creates a T, which is a ZIO, which as dependencies needs a mount point, which we see here is just having a parent. And it needs a scope as well. So we need both in order to do something useful with a modifier. It cannot fail. So there goes part of the presentation. And it gives us a T. And as it says already here, and I'm not sure about this. I might come back to it. But I kind of said here that, okay, this stuff never fails. And it's more laziness, because if you look, again, I'm going to take IndexedDB as an example. If you look at the actual failure modes of IndexedDB, it's a combination of what the documentation says, how it might fail, how it actually fails, and then stuff that I haven't seen yet, which is a combination of errors that happen in JavaScript features and exceptions that happen in the actual code. And I'm sure somebody could go in and create a those cases and make a nice error type for that, like, hey, if you do IndexedDB, then it might fail in this way. I could not be bothered. But this needs to be fixed if you actually want to do that. Yeah.
Isn't it more interesting to put any instead of nothing there?
Yes, so the short answer is no, it's not. It's the wrong type. Because any actually says, if you put it into plain English, this may fail with anything, right? I'm not going to tell you how it fails. It's a secret. It can be any type. That's what it says if you put any in the type. It's a little bit like in the Java world these days, if you call a method, because everybody hates checked exceptions, basically any method can fail with any subclass of runtime exception. You don't really know how it's going to fail. If you used the Kafka client, Kafka has one base type called Kafka exception, which extends from runtime exception, which has about 26 other very specific, nicely modeled exception types. Except you don't know which of these 26 you can expect if you create a new topic. Like, how is it going to fail? I have to think to yourself, yeah, it's probably going to fail. With, there might be I/O things that go wrong. Maybe the topic already exists. It's not going to fail with producer timeout exception, because we don't have that. And that's sort of any. Like, I'm not going to tell you what it is. Where if you use nothing, that is the promise that it doesn't fail. But in our Kafka example, like, it will fail with nothing. It will never fail. Hold on. If there's a little bit of time, I'll go into the type slides at the end. But I have to sort of check where we put the time. I want to get into some more specifics. Yeah. So please hold the thought, or ask me afterwards if we end up not having time. Yes. So we have this modifier abstraction. So let's try and do something simple. Create some elements. So. Let's have a class called createFn, create function with a name. What you might not know, in Scala, if you have an object that has an apply method, so instead of saying object.apply this or that, you can just write object parentheses this or that. So you can treat any object as a function, which makes things a lot nicer generally. Which is what we do here. We have a class createFn, which just has a name, has an apply method that takes a variable argument list of other modifiers, and then gives us a modifier that creates whatever element it is that we promised we would be creating there. We could create a createFn for diffs, we just call diff. We create one for input that we call input. And we can write some code that is a diff and then another diff, and inside that we want 2 input elements. And if we imagine some implementation that then goes into the DOM tree and says document.createElement something with this name and namespace and other things, you can sort of half see this working. Except what we would also implement is that if our thing goes out of scope, we go back in and delete the element. So keep that in mind. This is not just creation, this is also deletion. Now, just having elements is a little boring. We need attributes as well, which we can do in a similar way, except now let's just use a operator method. Again, in Scala, you can define new operators just as methods, and if they consist of symbols, you can use a space syntax rather than a method call to call them. So if we create a method that consists of a colon and an equal sign, then we can just invoke that method by having object, space, method name, space, and then the value. It's a simple way to create custom operators, which I figured looks a little better here than the apply thing. But again, it's subjective. If you like it the other way, then you can turn it around. Which again, you can imagine in the implementation, if we go in and run that particular ZIO instance. Remember, we have the mount point, where's the parent, so we could go into the parent and say parent.set attribute with the name that we have here and the value that we got over there. And that's how we could put this together. And technically, if we remove it, we could sort of remove the attribute again if we wanted to do that. You with me so far? Let's make it a little more complicated and add event handlers, which I'll, given time, skip over the definition. But what we can now write is another ZIO construct where we just say onClick. And the onClick method allows us to do something with events that happen on that particular parent. And for each event, we are allowed to do any kind of ZIO calculation as long as it doesn't create any errors, because we promised that there would be no errors. In this particular case, we just take the event and print it, but we could do something more useful with it, because it's like a mouse event. You get coordinates and other things that you can use with it. And we can do that directly in the registration. And remember, since this is a ZIO, this will register the event handler as it's created over here, but it will also remove it again when this particular ZIO goes out of scope. Now, this has until now been fairly static. All our code was just directly creating a div here, some input here, and the attributes are that. It can only be created this once. We're not changing stuff around yet, but we've built this all around ZIO and scopes and stuff. So let's try and create something so we can actually change some attributes. For that, I'm going to introduce a type alias again. I've not talked about ZStream, but if you know reactive streams or something similar, a ZStream is a little bit like a ZIO, except it can create more than one value. So it's a thing that has some dependencies, in this case scope. It might fill with an error, which is nothing. And it's going to give us 0 or more values of t at some point in time. Which is nice, because, hey, what if we could take such a stream and make that our attribute? Then whenever that stream gives us a value, we actually want to change the attribute to reflect that. So if we have a place where we can store a message, a subscription ref is a ZIO data structure that is basically like a variable, except you can subscribe to changes to that variable. So whenever it gets a new value, you can be notified that, hey, there's something new here. And you can be notified in terms of a ZStream. So you can get a ZStream to changes to that variable. And then somebody can come in from somewhere else and say, well, set this to whatever I set it to, and then everybody who's subscribed to it will get a notification. It's a little bit like an atomic reference, if you know that from Java, except you can subscribe to changes to it whenever a different object is put in there. Well, if we have that, then we can now say, well, let's create a div, and the actual text content of that div we want to get from that message object that comes in, where we can see it as a ZStream. And now we have something that can dynamically update itself from changes. I'm going to try skipping over some of this and show a little bit more about the application itself, given that the time is pressing. I hope I can make it. Who of you have never heard of event sourcing before? Good, because that's how the application is built. I'm also going to completely skip over the backend and just touch on some syntax and things, how they are solved, some particular use cases on the application. So if we go back here, you might notice that there are a couple of tools in our toolbar. There are 4 tools here, and then when we press a tool, the pop-ups that you see here, they kind of change, and whatever is represented as well. And of course, it changes also what happens if you mouse over. So there is some state somewhere that captures which tool is currently selected. So let's introduce our tool. Like there are 4 of these tools, and each tool has a key you can press to activate it, a name, some hint pop-up thingy, an icon, and a way to render it. And you might ask, okay, what is it that's being rendered? But that can be lots of things. Remember, a modifier is just a ZIO instance, so it doesn't actually have to render one div element. It can make arbitrary changes to our DOM tree and put all of those in the scope that is active together with that ZIO, so that if we switch to a different tool, anything that we have invoked there will automatically be cleaned up. So no matter if we make changes to the left here, or we make, oh, it's apparently disconnected again. If we make changes to the left, or we change how stuff is rendered, or maybe we have other pop-ups, if we select things, any changes we make are tied to that same scope object, so they will be handled as one scope together. And if we again use subscription ref to hold on to, okay, which tool is currently selected. Now we have a library function called mount1 that will take a Z stream of values. In this case, our selected tool, which is just our subscription ref, or whenever that changes, we get a new value there. And a function that will take take one of these values and turn that into a modifier, which is our render function. And mount1 will provide a scope for the current value, and automatically, when a new value comes in, delete that scope. So anything it did is cleaned up, create a new scope for the new one, and start rendering that. And that turned out to be really nice and simple to work with, because it means you can just go wild and just crap anywhere over the UI and put bells and whistles anywhere, because they'll all be tied to the same scope, will go away. But remember, it's not just state, we can change that way. Let's see if I can actually go into this directly. For this actually, let me see if I can bring this up. There's one tool here, which you can see a couple icons here, and there's actually an SVG library in this application with a couple thousand icons I ripped from somewhere. And you have sort of some incremental search for icons. So if I search for DK, you could just get one flag. But if I search for a flag, you can see there's a whole bunch of flags of all sorts of weird and wonderful countries. And there's a lot of it. As you can see, while I'm typing, these things sort of dynamically load. And I was hoping my phone connection would be slower so I could better demo it. But while it's loading and rendering these things, if you keep typing, it will abort that rendering and start a new rendering for whatever new results there are. And I'm not doing anything special for that, because the background fiber that is iterating through these icons and rendering them is part of the same scope that renders this dialogue and everything else. And if I just go to a different tool, all of that, the HTML elements, the background processing, the REST request underneath that, the connection to the index DB that stores some caches, all of that automatically goes away. And it will keep doing that. So there's a lot of safety to this aspect. And to sort of wrap up with, that safety is something that I hoped to find. I've gotten that safety while using ZIO on a lot of production backend software in the past few years. To share one anecdote, in Kafka, again. In one system, we used Kafka for general communication, as one does, but we also used it to log some debugging performance-like events, and just some topic, like we might want to look at this. And the ZIO abstraction does have Kafka exception as a error type there, which kind of means if you want to call that, you need to, just like with checked exception, decide what do I do with this error if it occurs. Which is nice to be triggered, because in this particular case, it was a debug logging thing. So I decided, with like 2 seconds of brain thought, yeah, this is logging. So if an error occurs, I'll just log a warning in our log4j and just forget about it. And that happened. So part of that particular topic went down, the rest worked perfectly, and the application kept running because somebody forced the developer to make an actual choice there. It's like Java checked exceptions wanted you to do, except now you've actually correctly solved a scenario that you thought, there's not going to happen. Kafka is like 15 million servers, it's never going to go down. Yeah, well, things might happen. And that kind of trigger has really made me consider error handling much more serious in writing systems. So thanks for your attention.
Tusind tak, og du er også heroppe, hvis man vil komme op og diskutere et eller andet. Det er jo tydeligt, at vi bare lige har skrabet lidt i overfladen af det her, men min gut feeling er, at det er sådan de rigtige byggeklodser til at løse den her problemstilling med en høj grad af parallelitet, specielt når der kommer mange brugere på det fine whiteboard, der begynder at arbejde samtidig, så kan det gå grueligt galt, hvis man ikke har begreberne i orden. Så tak for det.